Okay, good morning everyone. We are discussing today grade 12 first term test exam MCQ paper of Ananda College, Colombo for 2027 A-level batch. Okay, that means your batch. So this paper contains 25 MCQs. I'll share that one with you. And these questions are kind of moderate to easy level questions. We'll see how it goes. But anyway, this is a good opportunity for us to practice these or revise these first three lesson theories again. Okay, we'll see how it goes, right? So let's start from the first question. So the first one, it's asking false statement among the following relationships. Okay, so there are 5 scientists, right? And the related discovery or invention is given in front of them. For example, the Becquerel, right? Becquerel is the one who discovered radioactivity, so it is correct. And then you can write who are the other scientists that are linked to this radioactivity, right? You can write in our syllabus, you have the name Ernest Rutherford, because Ernest Rutherford is the one who identified alpha, beta, gamma particles for the radiation. Okay, you can write that one in front. Okay, then Aston. Okay, so that discovery mentioned for Aston is wrong. Okay, so Aston is our answer, right? So Aston and Thomson, they both joined to actually invent mass spectrometer. Okay, mass spectrometer, and then they discovered the isotopes of neon, right? So J.J. Thomson, the third answer is correct. And then not only J.J. Thomson, Aston, okay, also a part of that discovery. Understood? You have to write the name of that their invention. It is mass spectrometer. Okay, right. Then in front of Aston, something is mentioned. Okay, so let's see who is the scientist associated for the one described in the second answer. Let's read it. Discovering the number of positive charges in the nucleus increases by 1 electron unit. So that is what we call as Lamai atomic number. So atomic number was discovered by, okay, introduced by, not Aston. It was discovered and presented by Moseley. Okay, Moseley. Understood? So that's why the second answer is wrong. Okay, now what you need to write there, Aston is related to discovery of isotopes, and the one given in the answer of Aston is actually discovered by Henry Moseley. Okay, right. Then the fourth and fifth answer is supposed to be correct, right? See, look at what is given. Einstein, deducing that the energy emitted from metal surfaces behave as radiation emission from the metal surfaces behave as small energy packets, right? So then you can write underline small energy packet and write there was a name for this one. Einstein called them as photons, P-H-O-T-O-N, photons. Okay, so earlier it was called as energy packet quanta by Max Planck, but Einstein kind of gave a new overview to this one, right? So he called this one as particle of energy. Okay, you can write that to photon and put a dash and write particle of energy. Okay, and then last one, Dalton. Yes, of course, he's the one who proposed the first scientific model for the atom. Okay, golf ball model. Like that, you can see how it goes. Okay, so this is not a new thing for us, right? So there are like 15, 20 scientists in our first lesson. And just remember their names and their discovery. Okay, so it's a typical first MCQ that you will see even in your own term test. Okay, so study this part and yeah, don't get mixed up. That's my advice, right? Right, let's go to the second question. It's a bit of a good one. See, the de Broglie wavelength of an electron moving at the velocity v naught is lambda naught. If the kinetic energy of this electron is increased by 5 times. They have given the formula for the kinetic energy. This is a very similar question to the 2020 A-level MCQ, right, which we did in the class. And it says, anyway, asking if you increase this kinetic energy by 5 times, what would be the new de Broglie wavelength? Okay, right, let's see how to do that one. So there is an electron which travels at v naught speed, and its wavelength is lambda naught. And you are increasing this kinetic energy by 5 times. Let's say right now its kinetic energy is E naught, let's say. Then when you increase this one by 5 times, this becomes 5 E naught. Okay, then you need to find what is the new speed of this one. Then only, let's say it is V1. Okay, then only you can relate that one to the lambda 1 new wavelength. Understood? So then there are two formulae involved here. First one is to link kinetic energy and speed, which we already know from O levels. What is that equation? Kinetic energy is equals to half mv square. Okay, half mv square. Then the other equation is for the de Broglie wavelength. De Broglie wavelength is equals to h over mv. M is mass, v is the speed, right? Lambda is the de Broglie wavelength, and h is a constant. It is Planck's constant. Okay, so now you need to reuse these two equations and get the answer. Okay, so now let's see. So don't get confused here. It's a very simple thing. If you check our theory note for the 2020 A-level MCQ Lamai, I explained the question in 3 methods, right? So there is a long derivation method and there's a simple thinking method also, right? So I'll do both methods there. There was a third method also, kind of a similar in-between thing, proportionality thing, right? So I'll do that one. Just to remind, okay, this is a good question anyway, right? Energy, kinetic energy is proportional to the square of the speed, because the m is constant. No, it is the same electron we talk about. So here also m and h both are constant. And then, like I said, wavelength is inversely proportional to the speed. Okay, inversely proportional to the speed. So then you can simply do, you have to match these two, no, somehow. So then take your velocity, speed will be proportional to the root of the kinetic energy, isn't it? Then you can put that term here. Understood? Because it will be proportional to the root of the kinetic energy. So therefore you can finally eliminate this speed and take it is proportional to 1 over kinetic energy. Understood? So that's very simple. Then what you need to do is make a formula. That's better, right? I'm advising you to not to get wrong, right? So you can think and get the answer also, but it's a small risk behind that. So, but just try devising a formula. You have done it before. In gases lesson, you have done it. Remember? Pressure inversely proportional to volume. So then what did we do? P1 V1 equal P2 V2. So these are inversely proportional, means their product is a constant. So then you can write like this. Just remind this one. It's not necessary for this question, but just remind. And there is a similar relationship, no? So then write lambda 1 E naught E1 root equals to lambda 2 E2 root. There are many methods, but it's a good suggestion for you, okay? Then the first one is lambda naught, and energy is E naught root. And then you have lambda 1 that I mentioned here, and then E2 is 5 E naught root. Now you can see E naught root get cancelled, and what you will be left is the root 5. So then lambda naught equal lambda 1 root 5. So therefore if you then your lambda 1 will be lambda naught over root 5. This is your answer. Okay. Then the thinking process. That also very simple. If you master these things, I know these are not that difficult, but still you can tell just Take the answer within your head. It's not a problem, okay? So now just think here. So if you increase the speed by some amount, okay, so kinetic energy by some amount, right? Then it will be affected to the speed as a root, right? Now let's say simply, there is a particle that traveling in the speed of v. If their kinetic energy is E. If you double the speed, then kinetic energy will be multiplied by 4 times. Okay, just think. Just kind of establish the point, right? So then that means whatever the thing you multiply the speed, it will affect it, kinetic energy. It will affect the speed as a root. Okay, so that means this is the root of 4. Understand? So then think, if you multiply the kinetic energy by 5 times, okay, so the root of 5 is this, no? Okay, so root 5 will increase the speed. That means the new speed will be root 5v. Now here it was the root 4v. Now just think, start from somewhere which is comfortable for you, right? And then think about the root. Okay, then get the de Broglie equation. De Broglie equation says lambda inversely proportional to speed. That means if you increase the speed, lambda decreases. So then your lambda should be lesser than the previous value, lambda naught. And if you check the answers, I think there are only 2 answers that are having lesser values than lambda. Then only one contains root 5. Okay, only one contains root 5. So lambda will be equal to lambda naught divided by root 5. Very simple. Because they are inversely proportional, no? So if you increase the speed, velocity decreases. That's it. If you double the speed, if you increase the speed, wavelength decreases. If you double the speed, then wavelength become half. So if you multiply it by root 5, then wavelength become a fraction like this. So it's very simple. Think and get. Okay, and whatever the method you prefer, try both and practice. Okay, Lama, I hope you understood the whole picture, right? So that's our answer. Let's see what is the answer. Answer is answer number 4. Okay, answer 4. So practice it well, okay? Practice it well. Then look at the third question. Right, third question. The number of electrons in manganese atom with quantum numbers L equals 0 and Ml equal plus 1. Okay, L equals 0 and Ml plus 1. They are asking for the manganese atom. So in these kind of questions, what we need is first, we need their electronic configuration. So manganese, let's write the electronic configuration. Okay, let's write. Then let's later find out how many electrons are according to this condition they ask. So manganese electronic configuration, atomic number is 25, right? So it is not given here, but you can refer the periodic table that will be given to you in the exam. So electronic configuration is this: 1s2, 2s2, 2p6, 3s2, 3p6, and the other electrons, 7 electrons will be there, like 3d5 and 4s2. This is how we write. Okay, and then L equals 0. L equals 0 means S sub-energy level, S orbitals. Okay, so there are these electrons, actually 8 electrons that are in the S sub-energy level. Okay, so 8. And then Ml plus 1. Ml refers to for the orbitals. So in the S sub-energy level, P, D sub-energy levels are here, no? So for S sub-energy level, you have only 1 orbital, right? And for the P sub-energy level, you have 3 orbitals. For the D, you have 5. And for Ml values relevant for these orbitals, here it is 0, only 1 orbital. And -1, 0, +1. And -2, -1, 0, plus 1 and plus 2. This is how we write now. So then Ml plus 1 you can find in P sub energy level and D sub energy level. Here you have those two orbitals, right? That means if it is P6, two electrons will be according to Ml plus 1 condition. Okay, if it is D10, two electrons will be according to this condition, but here it is not D10, no? It is D5. No? That means one electron is filled per each orbital. One electron is filled per each orbital. So there's only one electron that satisfies that condition. Understood? So then check your formula, then check your electronic configuration. And here you have two electrons according to the condition I said. And here P6 again there, another two electrons. And only one electron from here. So how many total electrons that follow this condition? 5 total electrons. Understood, Lama? It's not a difficult one, but still a good one, the exam level question. Okay, so now let's go and see what is the answer. 8 and 5. 8 and 5, answer 4. Okay, answer 4. 8 and 5. So there are 8 s electrons. Okay, and 5 Ml plus 1 electrons. Right, so just refresh your knowledge about quantum numbers again. In previous papers also we did that one in our evaluation test 2 discussion, remember? Okay, so then this fourth one. The compound with the largest bond angle is. Okay, so now it's from the bonding lesson. There are 5 molecules given. They're asking for the highest bond angle. Okay, so now let's get their structures. CCl4 is a tetrahedral molecule. So their bond angle will be exactly 109.5 degrees. It is tetrahedral. Okay, tetrahedral. And then the next molecule is NH3. NH3 also a tetrahedral electron pair geometry molecule, but its shape is trigonal pyramid. So there is a lone pair that is pushing the bond pairs. So then the angle between bond pairs will be a little bit lower. So how did we figure out this one? We subtracted 2.5. This is just some rough value. It's not a hard and fast rule. So just some rough value. So then it will become 107 degrees. Okay, just know that is enough. And then the next one, water. Just like in NH3, water is also having lone pairs, and it is having 2 lone pairs. Okay, so then the push will be more because a lone pair are also having a greater push. So then as a result, bond angle decreases further. So how did we remember this one in the class? We subtracted 2 times 2.5 because there are 2 lone pairs. So 1 lone pair, 2.5. That's how we remember. So it is 104.5 degrees. Okay, and then so far this is the lowest angle, right? So let's wait. And the other one is NO2 plus. NO2 plus. This is the bond structure, and you can see it's linear. So 180 bond angle, no problem. Largest bond angle. And NO3 minus. This is the Lewis structure of NO3 minus. Actually, not the Lewis structure. I didn't show the lone pairs, right? But however, this is enough for us. And don't say the bond angles are different. So because this is not the real structure. Real structure is a hybrid of all the resonance structures of nitrate. So there are 3 resonance structures for the nitrate. And when you are talking about the bond angle, you have to think about that structure. So minus 2 over 3, minus 2 over 3, minus 2 over 3. This is a closest structure for the resonance hybrid. Okay. So then you can see the repulsion units are same. So bond angle will be exactly ONO bond angle will be exactly 120 degrees. Don't say it is less than 120. It's wrong because you have to think about the hybrid. Get the idea? Okay. So what is the one with the lowest bond angle here? Sorry, not the lowest. They're asking the largest. So largest bond angle is, of course, we figure out that one earlier, this NO2 plus. Okay. So then you need to have a good idea regarding how to draw the Lewis structures here too. Right. So if you missed a Lewis structure, anyway, you can get wrong. But I think now by now you're all familiar with that one. So for example, CCl4NH3, water, nitrate, those molecules you may get used to draw. So no need to follow the Lewis method, then just remember and draw. But everything I said comes with the practice. So if you're still struggling to get the structure, so at least start now practicing. Okay, so then within few months you'll be able to draw these structures without the Lewis method. I mean, you are already memorizing the structure. Okay, you can do it, right? Don't start memorizing structures, okay, right now, but it comes with the practice. I hope you get what I'm telling. Okay, right. So then the fifth question, it's asking the non-polar molecule with polar bonds. See, it's a kind of like a good question, right? Non-polar molecule with polar bonds. So non-polar molecule, what is the meaning of that one? So if you don't have that molecule doesn't have a net dipole moment, resultant dipole moment, then it becomes non-polar. Okay, it becomes non-polar. Okay, we'll get the 5 structures and then discuss. So the 5 structures are water, then you have O3, NH3, BCl3, and HCN. These are the 5 structures. These are the 5 structures. Yeah, for the earlier question, answer is answer 4, NO2 plus. Okay, so I'll tell the answers from the beginning. For the first one, answer 1. For the second one, answer 4. Third one, answer 4. Fifth one, also, fourth one, also answer 4. Okay, right. Now we are discussing the 5th question, right? Okay, so then look at this again. They're asking the polar molecule with, non-polar molecule with polar bonds. So, for example, let's start with water. So, this is the Lewis structure of water, right? And there are 2 bonds, 2 OH bonds, and we are marking something like this. Remember, this is called dipole moment. It shows you how the bond is polarized, right? Bond electrons are how they are pulled towards some direction, right? And then for the lone pair also, you have a small dipole moment. So then the resultant dipole moment will decide whether it is polar or non-polar. So this molecule water has a resultant dipole moment towards this direction. Okay, so it is going to be polar. Let's take this BCl3. BCl3 in the other hand, it is a trigonal planar molecule, and the bond angles are exactly 120. And then the chlorine is more electronegative than boron. So there are 3 dipole moments like this. So you have learned even in physics, if you arrange these 3 120 angle equal forces, okay, so dipole moment is not a force, but let's assume it's a vector quantity, anyway. So if you arrange these vectors in these angles, the resultant is mu r, resultant dipole moment is 0. That means it is non-polar. But you can see there are polar bonds. That's why we mark a dipole moment at the first place. So this is a molecule that satisfies the given conditions. Okay, so then answer is answer 4. BCl3 again, answer 4. Understood, Lama? Right? So then as extra thing, just write something about N2, O2, and H2 like that. Why? Because those are also non-polar molecules. Okay, and these are non-polar molecules. Non-polar molecules with non-polar bonds. Non-polar bonds. So bond is also non-polar. So you don't mark a dipole moment because electronegativities are same. So there is no pulling from one side. Okay, so remember that too, because these are the 2 types for the non-polar molecules. The molecules with polar bonds and molecules with non-polar bonds. So, but both are As a molecule, non-polar, no resultant dipole moment. So why it is important to know this? Because these non-polar molecules, right? They can form only one secondary interaction. It is London forces. Okay, so London forces only. That's why. So it is important when we are deciding the boiling point, comparing those properties, right? So it's important. So remember, first you need to get the Lewis structure correctly, and then you need to get the VSEPR theory and get the shape of this molecule, proper shape, and then you need to decide. There's a lot to process in this question. So that's why some students are finding this difficult, because if you have any problem in the previously mentioned theory areas, you will not be able to get the correct answer. That means you need to practice again Lewis structure, VCPR theory, dipole moment, everything. But not difficult. Take step one by one. So then you will get there. Okay. So start now. If you are still struggling with the second lesson, it's not a bad lesson. It's an easy one, but do at least take few steps right in this week and see how it goes. Okay, and practice again these questions. We have done these questions several times. I mean, more than 10-20 times we have done this. Okay, so repeat. And what about the other three questions, other three answers? O3. Ozone, this is the Lewis structure, right? But actually, this is a hybrid of these two structures, right? So then you have to talk about the real ozone. So real ozone is still polar. It's a polar molecule. And it is having non-polar bonds. These are non-polar bonds. But molecule is polar. Polar molecule. Why? Because there is a dipole moment that is not cancelled from the lone pair. Okay, so this lone pair is having a small dipole moment now. So therefore, we can consider it as a polar molecule. Okay, so also important, right? And then NH3, a polar molecule with polar bonds, just like water. Okay, here the dipole moments, and the resultant dipole moment is upward like this. And HCN is the Lewis structure of HCN, and you can see everything is pulled to one direction this way. So it's a polar molecule with polar bonds. Okay, so write a good review. Will help you to revise polar, non-polar, everything. Okay, Laman. So answer 4 for the 5th question. Then let's go to the next one. 6th question. The relative molecular mass of the compound containing only carbon, hydrogen, oxygen is 90. So it's a good question anyway. You can see according to the given data, it is from empirical formula and molecular formula. Okay, so it's a common question for the first time test. Let's see how to do it. There is a fast method and a short, kind of a longer method too. I'll tell you both. So first it says carbon dioxide 44 grams, and then water 22.5 grams are given, and then the relative molecular mass is 90. Okay, and it says this compound contain carbon, hydrogen, and oxygen too. Let's write it as CXHYOZ. Right, and it's asking the molecular formula of the compound. Molecular formula of the compound. Okay, molecular formula of the compound. Right, so the long method is this. First of all, find the number of moles of carbon dioxide. Moles of carbon dioxide, what you should do, divide this 44 grams by the molar mass of carbon dioxide. So for that, you can add and see. Carbon 12, oxygen 16, 16 times 2, 32, 32 plus 12, 44. So then you can see it is also 44. And then 1 mole is there. And then go to the moles of carbon, because all the carbon that was there in the compound is converted to carbon dioxide. So if you have 1 mole of carbon dioxide, there must be 1 mole of carbon in the sample. Okay, so they have given us the mass we took for this experiment is 22.5 grams. So within this 22.5 gram, you have 1 mole of carbon. Understood? And then do the same thing for water. So find the moles first. So you have to divide 22.5 by 18 grams per mole. Let's hope it is divisible. So 22.5 divided by 18. So 18, you can divide this one by 2 first, 9. And then this becomes 11.25. Now let's divide 11.25 by 9. So you have 1. So 22 left. And then you have 2, 18 left. And 4, 45, you have 5. 1.25. 1.25 moles. And then the thing is this. If you have, let's say, let's take the CH4. CH4, when combusted with oxygen, it gives 1 carbon dioxide and 2 water. Why 2 water? Because you have 4 hydrogen. So that divided by 2 and become water molecules. Now because altogether you have 4 hydrogen atoms. Okay. So that means if you have some number of moles of water, there will be twice like that hydrogen. Understood? So then apply the same thing here. So then moles of hydrogen will be 2.5. Okay, moles of hydrogen will be 2.5. Now you got the moles of hydrogen and carbon. Then there is another element left, no? Oxygen. So how do we get the moles of oxygen? This is how you do it. First find mass of oxygen. Mass of oxygen. So for that, 22.5 minus the masses of these two. So 1 mole of carbon means 12 grams. 2.5 moles of hydrogen means 2.5 grams. So that is altogether, that is what? 14.5 grams. So subtract that. Then you will get 22 minus 14. You get 10, 12, 8 grams. Okay, so then find the moles of oxygen. Moles of oxygen is equal to 8 gram divided by 16, 0.5 moles. Okay, so now you know the moles of this compound. So in this method, the next step is getting their carbon, hydrogen, oxygen molar ratios. Molar ratios. So molar ratios are, here this is 1, this one is 2.5. 2.5. This one is 0.5. So to get the simplest ratio, you divide the whole thing by the smallest number. Smallest number. So then you will get 2, 5, and 1. So then it becomes empirical formula C2H5O. This is your empirical formula. Okay, so then find empirical formula mass. So it's a long method, right? So you can see how it goes. Still I'm doing the question. There is a small shortcut too. I'll show you that later. So anyway, it is 24 plus 5, 29. And 29 plus 16, 35, 45. 45 gram per mole. This is the empirical formula mass. Then they have given that relative molecular mass. No? So then find out what is the molecular formula using this equation that you have seen. Remember, relative molecular mass or molecular formula mass is equal to n times empirical formula mass. Okay, so now you know the empirical formula mass, therefore you can find n. 90 divided by 45, which is 2. Okay, so therefore your molecular formula is what? Molecular formula is the 2 times like this. 2 times like this. So it becomes C4H10O2. C4H10O2. So that answer is there as the answer 4 again. Answer 4. Okay, so what's the short method? The short method. Okay, so mass of carbon in the total mass as a fraction then will be equal to the mass of carbon in total compound. So 19. So think about that. Okay, so mass of carbon is 12 and total compound mass is 22.5. That's a fraction, and this fraction, these two fractions are equal. Okay, and then the mass of carbon in the total compound, that is what we don't know. And we know the relative molecular mass is 90. And simplify this, then you will get the mass of carbon in the whole compound. If you, in a 1 mole. So this box is written for 1 mole. Okay, so mass of carbon in 1 mole. Right? And then simplify this one. You can find M equals 12 over 22.5 into 90. Okay, so now this is supposed to be divisible. Let's divide this one by 2. This is 6 and this is 11.25. And then you can divide this one by 9. Yeah, and divide this one by 9. 11.25 divided by 9. We did this one earlier. So 1 and 9, 22, 2, 1.25. It is 10 and 1.25. Okay, so then to get a, yeah, let's multiply, it is like 60 over 1.25. Okay, so then let's multiply the whole thing by 4, and it becomes 5, and this becomes 240. Okay, and then yeah, and this becomes then 1048. 48 grams is there of carbon is there in 1 mole. Understood? So then that means 4 moles of carbon in 1 mole of compound. So then there's only one, there are 2 answers that are starting with C4. And then do the same thing for the hydrogen. Follow the same process for the hydrogen. Understood? So don't kind of try to memorize these methods, but you can think and understand. See, how did I get this one? Mass of carbon from the total mass they have given, 22.5. This fraction should be equal to the mass of carbon and the total compound mass of carbon in 1 mole and mass of 1 mole. Okay, so these should be equal fractions. Then by simplifying this, you can find how much mass of carbon is there in 1 mole of compound. So that is 48. That means 4 moles are there. So then C4. Answer should start with C4. And do the same thing for the hydrogen. Okay, so how did we write it for the hydrogen? So mass of hydrogen is 2.5 grams. No? Anyway, you are finding the moles here only, you have to do that. So 2.5 grams over 22.5, okay, is equal to then mass of hydrogen in the compound and 90. Then follow this one. Simplify and find the how much mass of hydrogen is there in 1 mole. You will get 10 grams here. Should get 10 grams. So let's see how it is getting. So this is divisible. There will be 4, 8 and 9. 9. And will be getting cancelled. 10 here. Then MH equal to 10 grams. So 10 grams means there will be 10 hydrogen. Okay, so 4 carbon and 10 hydrogen. There's only one answer. C4H10 and oxygen sum amount. Okay, answer 4. Answer 4. So that's how you do it. And you can, if you want the oxygen also, can do the same thing, because here we are finding the mass of oxygen, can do the repeat the process. So my advice is don't try to memorize, but anyway, you can follow the long method. This is the one we learn in the lesson. Finding the mole, simplest ratio, and empirical formula, molecular formula. That's the usual path. But there is a shortcut too, if you think. Okay, I hope you all understood that question. Not a common question in the A-level paper, but still they are in the term tests. Okay, Laman? Okay, so answer 4 again. Right, go to the 7th question. The IUPAC name of CuCl. Okay, CuCl. Right. I'm going to erase this and I hope you note down whatever the things you need. IUPAC nomenclature of simple compounds was done under chemical calculations. Okay. And we'll be discussing IUPAC nomenclature in several other places in our syllabus. For example, under D block, organic, we'll be discussing. So it's a kind of a systematic process that we use to name any given compound. Okay, so everyone in our community, science community, use this method. So everybody will name the same compound with the same name, so no confusions. So for that, there are rules. Okay, so CuCl. Let's see how to break down this one. In CuCl, don't mind about the copper yet, but think about Cl. It is always Cl minus. There are no other possibilities for the Cl, because it must take one electron to become noble gas configuration, to have noble gas configuration. And if this is Cl, then Cu plus be Cu plus. So Cu must be Cu plus. Understood? So then actually this compound contains copper plus and Cl minus. So copper plus, the IUPAC name is copper 1. Okay, in systematic nomenclature earlier, the early nomenclature, trivial nomenclature, we call this as cuprous. But in IUPAC nomenclature, you must call it as copper 1 ion. Okay, so copper 1 ion. And this is what? It is simply chloride ion. Chloride ion. So the compound must be, but copper 1, chloride. Space chloride. This is the answer. This is the answer. Copper 1 chloride. So let's see which answer gives that one. Copper 1 chloride. See the answer 3. So don't say cuprous. Cuprous chloride is also the correct answer. I mean, it's not according to the IUPAC nomenclature. Okay, it's for the trivial nomenclature. Right, copper 1 chloride. Easy question. Go to the next one, Lama. Electron pair geometry and the shape around the bromine atom in BRF5 molecule. BRF5 molecule. Okay, so just to revise Lewis method in this paper too, I'll use it. Anyway, so I drew some structures earlier. I didn't use the Lewis method, but for someone who need the Lewis method, I think I should revise it. So first of all, get the skeleton. There will be 5 molecules around this, 5 atoms of fluorine around them. And then find the total number of valence electrons. So bromine, fluorine, they all in the group 17. Group 17. So group 17 electrons are having 7 valence electrons, just like fluorine, chlorine. Bromine should also have 7 electrons. So 5 fluorines will give you 7 into 5, 35 electrons, and another 7 electrons from bromine. So altogether 42 electrons. From this 42, already we have represented 5 bonds. That means 10 electrons are represented. So that means 32 electrons are remaining to be represented. Okay, that means you have 16 electron pairs. From these 16 electron pairs, you can place how much? Oh, 3 electron pairs per each fluorine. So 15 electron pairs on fluorine. So there will be 1 electron pair remaining that must be placed on bromine. So this is the Lewis structure of BRF5. Then how to get the shape and geometry? You can see here around this bromine, you have one lone pair and then you have 5 bond pairs. So altogether you have 6 VSEPR units, or we can simply say repulsion units. So if you are having 6 repulsion units, its electron pair geometry is octahedral. Octahedral electron pair geometry. But you have one lone pair, right? So because of that, the shape will become square pyramidal. Square pyramidal. Okay, so shape is square pyramid. So I will draw this one. It's not that difficult. So draw 4 fluorine atoms in the same plane. So to indicate that they are in the same plane, you are drawing dotted lines. And then another fluorine here. Okay, and then the lone pair. Now if you connect these fluorine atoms, you will see that it is making a square base pyramid. Isn't it? Okay, so name is okay. So what's the answer? Electron pair geometry first, and then it's followed by the shape. Octahedral square pyramidal, answer 2. Answer 2. Okay, Lamai, I hope you got that answer correctly. Let's see. Yes, answer 2. Right. So not a difficult question, right? So there's another chemical calculation, a small one. Let's go to that too. If the mass of N nitrogen in X grams of ammonium carbonate, so don't worry about the name, but it was taught in the IUPAC nomenclature that I mentioned earlier, ammonium ion and carbonate ion. So ammonium carbonate is 49 grams. Okay, so it's asking the number of moles of this X. Right, so let's try to use this space. It's a small question. So how to do it? From the whole compound, right, ammonium carbonate. Okay, so this has X grams, X grams, X grams. And then only for the nitrogen, you have how much? 49 grams. Then you can find moles of nitrogen atoms. Okay, so 49 you have to divide by the relative atomic mass of nitrogen, 14. So you can see both are divisible by 7. So 7 over 2. You have 3.5 moles. 3.5 moles of nitrogen. But you can see this statement is very important. In 1 mole of compound, we have 2 moles of nitrogen. Okay, so that means you can find moles of nitrogen, moles of compound simply by dividing this amount by 2. Understood? So it will be 1.75 moles. See, not a difficult question. Just look at the relationship. In 1 mole of the whole compound, you have 2 moles of nitrogen. You have 8 moles of hydrogen. You have 1 mole of carbon and 3 moles of oxygen. Okay, so then you use the relationship. Okay, so half of the nitrogen moles you have the compound. So 1.75, answer is answer 4. Answer is answer 4. Okay, answer 4. Then go to the next question, 10th one. Another small calculation. So asking the mass of sodium hydroxide contained in 100 grams of 100 cubic centimeters of sodium hydroxide solution, and with a concentration of, so what they're asking, the concentration of 12 mole per decimeter cube. 12 moles per decimeter cube. Okay, so simply they have given the volume and the concentration. Okay, So these supposed to be O-level type questions, right? But anyway, let's see how to get the answer. So concentration is equals moles over volume, and then moles are equals mass over molar mass. So you can plug this term here. C equal simple M over capital M over V. So that means simple M over capital M V. Okay, right. So if you need the mass, simply you can do what? Simple M equals concentration volume into molar mass. Okay, so concentration is what? 12 mole per decimeter cube. Volume is 100 cubic centimeter cube. So 100 cubic centimeters means 0.1 decimeter cube. Divide by 1000 to convert it into decimeters, decimeter cube. Then the molar mass of sodium hydroxide is 40. Sodium 23, oxygen 16, and hydrogen 1. You add them, you get 40. So 40 grams per mole. You can see all the units get cancelled except gram. So you'll get the answer in grams. Okay. So this 0.1 and 0 you can cancel. So simply it is 12 times 4, 48 grams. Okay. You have that in answer 3. Understood? Or you can do this separately, right? You can use C equal N over V and concentration and volume, use them to find moles of sodium hydroxide. Then multiply that one by molar mass and find the mass. You can do it in 2 steps too. Okay, same thing, right? You can understand. So out of 10 questions, right? There were some good questions also and some easy ones too. And pay your attention more to the good ones. Okay. Then we are going to the 11th question. Which of the following includes only the species with 2 unpaired electrons? Species with 2 unpaired electrons. So I'll put the answers here. For the 11th question, you have titanium 2 plus. And then you have nickel 2 plus, cobalt 2 plus. These are the different ions we have. And vanadium 3 plus. And finally, manganese 2 plus. So all are 2 plus ions. Yeah, titanium 4 plus is also there. I think others we covered, right? Yeah. So let's find out how many unpaired electrons are there in each ion. Okay. So the fast method is just remember their configuration and then remove 2 electrons or whatever the number of electrons you need to remove to get the ion, and visualize the configuration. Okay. We call it as what is that electronic configuration? The orbital diagram. So orbital diagram, visualize the orbital diagram and see how many unpaired electrons are there. Okay, now let's see how to do it. So I'll get the titanium valence electrons, unpaired electrons according to that method. Okay, so titanium atomic number is 22. So then I can visualize, I can get the Lewis, electronic configuration. It is argon times 3d2 4s2. Okay, for titanium, this is for titanium. So when it makes titanium 2 plus, 2 electrons get removed. So titanium 2 plus is 3d2 because the last 2 electrons are always get removed. And how this 3d2 is distributed? 1 electron per each orbital. So there will be 2 unpaired electrons. So this is a correct option. Titanium 2 plus. Okay. And I like that, do the same thing for the nickel. And you can do it in that thing within your mind also, right? So nickel electronic configuration is, okay, it's atomic number 28. 28. So there's a pattern, right? So it's argon times 3d8, 4s2. So then nickel 2 plus is argon times 3d8. So how do you draw 3d8? Paired, paired, and paired. Only 1 electron here. So this is how 3d8 is drawn. And again you have what? 2 unpaired electrons. So nickel 2 plus is also the correct answer. Then again you can get this answer for the question even in the very first choice, right? So answer is going to be answer 1. And then for the review, write how many unpaired electrons are there for the others. Okay. And cobalt atomic number is 27. 27 is this atomic number, which was discovered by Mosley, remember, in the first MCQ. And yeah, it is 3d7 4s2. So then cobalt 2 plus becomes, the cobalt 2 plus is 3d7. So there will be 3 unpaired electrons. 3 unpaired electrons. 3. Okay. And vanadium 3 plus. Vanadium atomic number is 23. 23. So 3d3 4s2. So then for vanadium 3 plus, it is 3d2 because 4s2 and one of the 3d electrons are gone. So this is also the correct answer. You have 2 unpaired electrons, just like titanium 2 plus. But it is paired with the wrong one, I believe. Yeah, with Fe2 plus. I didn't write Fe2 plus. We'll check Fe2 plus. Iron atomic number is 26. So argon times 3d6 and 4s2. So when it makes Fe2 plus, it is just 3d6. 3d6, you have 4 unpaired electrons. This is paired and these 4 unpaired. So that's why vanadium is paired with the wrong one. Okay. Then go to the manganese. Manganese 3d5 4s2. And for the 2 plus, these last 2 electrons get removed. So 3d5, you have 5 unpaired electrons. Titanium 4 plus, 3d2 4s2. Right? So then to get 4 electrons, all these get removed and it has only argon configuration. So no unpaired electrons. Like that, write a complete review for the question. And actually, this is a good one. They can expect the same thing in your A-level paper too. Okay, so very exam level questions are there from first and second units. Third unit questions are also somewhat okay, but you saw some easy ones also there. Yeah, right. Anyway, I hope you got that right. Let's go to the next question. So 11th one again, answer is answer 1. So you're going to go to the next page. So I'll give you the printout of this paper in your next class. Dematagoda and Panadura classes, I had to give this printout, okay? So 12th question is from hydrogen emission spectrum. Hydrogen emission spectrum, okay? You can see spectral lines are given. For one direction, it is saying lambda increases, and it says again E line is blue color. So that means it is in visible region. Okay. So I'll put the same diagram in the board and discuss. Okay. Right. So this is the chart. A, B, and C. A, B, and C. And then after a small space, start D, E, F, and G. It's a good question, huh? It's a good question. And it says C is colored. Sorry, E is colored. E is colored. E is blue color. This one is blue color. This is blue. That means it is in the visible region. Visible region. So what is the series that is there in the visible region? It is Balmer series. So that's how you think. So then if this line is Balmer series blue color, So Balmer series is having red, green, blue, violet, RGBV. These are the lines for the Balmer series. Then the adjacent lines, you can guess the color. Okay, so according to this, you can say this is your red color line, this is your green color line, this is blue color, and this must be violet. Okay, so you follow this method. And then another point is there. Okay, wait. It says for this direction, what happens? Lambda wavelength increases. So, you know, according to the Planck equation, energy equals frequency into wavelength. Okay, energy equals frequency into wavelength. So, energy equals h lambda. So, h frequency. Energy equals Planck constant times frequency. Or you can say what? Hc over lambda. So now you know if wavelength increases, what will happen to the energy? It should decrease. Okay, it should decrease. So Balmer series is having a lower energy. So then the other series, this must be according to this, right? It is having high. These four lines are having higher lambda. So more energy. So more energy, then it must be what? Ultraviolet, UV. So what is there in the ultraviolet region? Lyman series. That's how you think. Is that clear now? What is there in the Lyman series? It is UV region, it is Lyman series. Right, now you can go to the statements. Now you got the clear idea about the whole diagram. So line C is colored. It's wrong. Line C is in the UV region, no? So it's not going to be colored. You can say it is in UV region. It is in the Lyman series, ne? So it's not going to be colored. Second one, to be colored, it must be in the visible region. Visible region wavelength is 400 nanometers to 700 nanometers approximately. Okay. So second one, all the spectral lines belong to the series in which line E belongs. Line E is the one they mentioned as blue color, Balmer series. So it says all spectral lines belong to the Balmer series. Belongs to the visible region of the electromagnetic spectrum. So what do you think about that? So only 4 lines are shown here, but it's not only 4, right? So all electrons that are falling to the second energy level belongs to the Balmer series. So, right, I'll draw it in the board and explain. So this statement is going to be false. You can understand by small thinking, you can understand it. Right, so let's draw the energy levels and explain it further. Draw some energy levels. This is not according to the scale. Anyway, this is your first energy level, second, third, fourth, fifth, and 6th energy level. And I have to draw 7th energy level also. 6th and 7th energy levels. Okay. So those who are falling to the first energy level are Lyman series. Okay. So here your line C and B and A. These are the Lyman series transitions. Okay, because you know this has low energy means, see, lower length. And then think about the same thing in your Balmer series. Okay, so G, red color line. And then F, green color line, blue color line, and violet color line. D, E, F, G. And then you can draw another line, right? I draw the 7th energy level too. So this one. So this one is in the more energy. So it is in the UV region. So actually, Lamine. So that also belong to the Balmer series, right? You have to understand, Balmer series is actually, it's partially visible. So telling all lines that are there in the visible region is incorrect. So it is partially visible. Understood that? It's a good question. Most students are selecting that as an answer. Yeah. Then the third one, line D correspond to the electron transition 5 to 2. Line D, 5 to 2. Line D, D. D you can see here it is 6 to 2. It is 6 to 2. Line D, sorry. Line D is 7 to 2. No, sorry, 6 to 2, 6 to 2, sorry, my mistake. Sixth energy level to the second energy level. So 3 to 2 is red. Okay. 4 to 2, 5 to 2, 6 to 2. So third one is also wrong. It says 5 to 2. 5 to 2 is not the D, it is E. Okay. So it is 6 to 2. Then look at the fourth answer. It's saying line A belongs to the infrared region. No, it's false. It is belong to the UV region. So answer 5 must be correct then. Let's see how it happens. It says the gap between F and G, this gap, is equal to the gap between A and B. So don't try to measure with a ruler or something. Just go to that diagram we draw. So you can say F and G are the first two lines of the Balmer series, and it represents this gap, the energy gap between fourth and third energy levels. Okay, and then go to the BC lines. Sorry, AB lines. AB lines are also showing what? Energy gaps of third and fourth energy levels. Understand? So that is correct. So it represents energy gap between, energy difference between n equal 3 and n equal 4. Okay, so this is correct. It's a good question, huh? A very good question that can be there in your own term test, and for the for the A-level paper also it's a good one. Right, so write a good review. So just try to remember how did I start the question. Okay, I start from this line and figure out this is BAM, and then since this part is having low energy and this part is having high energy, this must be Lima. That's the way of thinking. And when necessary, remember how to draw this energy level representation too. Okay, it will help us to get some answers like this. Okay, a good question, right? Let's go to the next question. 13. The correct statement regarding the following molecule is, so organic molecule is given. Anyway, don't worry. We only refer here about the bonds. H, C, triple bond C, C, and double bond CH. This is the molecule. So there are two hydrogen. Sorry. And let's see the 5 statements. I'm going to explain it at once. All 4 carbon atoms lie in a straight line. So all 4 carbon atoms lie in a straight line. That is wrong. But let me explain that. So you can see these carbon atoms are linear and 180-degree bond angle because they are sp hybridized now. And these two are sp2 hybridized. So it is going to be trigonal plane and 120 angle to each other. 120 angle around the carbon. Okay. So then let's try to draw this one. So if they arrange 180 angle to 180 angle, bond angle, with adjacent carbon, this one, these 3 carbon should be in the same line. This must be 180 now. And then around this carbon, it should be 120. Okay, so it should be like this. Now it's not the same straight line. It kind of bends here. And then you have other two hydrogen over here. So this is the way. The actual, kind of way of showing the bond angle. Here it's around approximately 120. Here also it is approximately 120. Why did I say approximately? Because there's a double bond and the bond lengths are also different. So it will affect bond angle somehow. Okay, here also it will be kind of change, okay, but anyway, I think we take it as 180 and 120. It's no problem. Small change. And so first statement is false. Only the first three carbon atoms are in the same line. Okay, first three carbon atoms are in the same line. So these are the carbon atoms that are in the same line. You can include this hydrogen also. sp hybridized atoms and their connected atoms are in the same straight line. And then what about the same plane? Okay, same plane. Same plane. All these atoms are in the same plane because I drew them in the board with showing angles. Board is a plane, right? So here they all in the same plane because sp2 hybridized atoms and their connected atoms are in the same plane, and sp hybridized atoms and their connected atoms are in the same straight line. Okay, so first statement is false, telling all four carbon in the same straight line. Go to the second one. Hybridization state of carbon atoms are different from each other. That's also correct. Wait. Different from each other. So there's a small confusion. Okay, let's leave it and see. Third one. Only three carbon atoms lie in a straight line. Yes, correct. Only hybrid orbitals are only hybrid orbitals are overlapped to form all the sigma bonds. No, here you have an atomic orbit. So example, this bond is formed with sp2 hybrid orbitals of carbon and one s orbital of hydrogen. So fourth one is false. 1s is used. Fifth one, equal number of sp hybrid orbitals and sp2 hybrid orbitals exist. Yeah, this carbon is wait, okay. So this carbon is sp, no? So there are, for this carbon you have two sp hybrid orbitals, and for this carbon also you have two sp hybrid orbitals. So altogether you have four sp hybrid orbitals, right? But let's see this one. It is sp2. So you have three sp2 hybrid orbitals. You can see now the answer is not correct. This also is having sp2 hybrid orbitals. So altogether you have how many orbitals? 6 orbitals. So it seems like correct now when you are reading. See, equal number of sp hybrid orbitals and sp2 hybrid orbitals exist wrong. Equal number of sp hybridized atoms and sp2 hybridized atoms are existing. It's a good question. Okay, made for you to get confused. Also, I didn't review about the second statement. No? Second statement, hybridization states of carbon atoms are different from each other. You have to take it as wrong. So here it is actually meaning all four atoms are having different hybridizations. Let's say one is having sp, another one is sp2, sp3, sp2, sp3d, like that. So it's not right. So two atoms are having equal. So it's not a great answer, but the most suitable answer is 3, right? Most suitable answer is 3. Okay, so you have to stick to that. So let's say here 2 is wrong. 2 sp2 and 2 sp. Okay. Right. Go to the 14th question. Shape of AO3 atom, sorry, AO3 anion is tetrahedral. AO3 anion, AO3 minus, sorry, anion is tetrahedral. The group to which A belongs to in the periodic table. They're asking the group that A belongs. So AO3 minus tetrahedral. So what is this? Tetrahedral. Tetrahedral. Okay, so let's try drawing this one. So in the Lewis structure, negative charge must be there on oxygen to become stable. Then other two oxygen atoms are forming double bonds. There will be other negative charges then. And to become it is tetrahedral. Shape is tetrahedral. Can't be, right? Yeah. Electron pair geometry can be tetrahedral, but shape, you can see only 3 atoms are there. Okay, wait, 3 peripheral atoms are there. Give me a second to check the actual paper. This is a typed one by me, no? So give me a second. That is AO3 minus. AO3 minus. It says the shape. Yeah, so it's a mistake, right? So let's correct it and get the answer. Let's say it is not the shape. Cut the shape and write. Let's see whether we can get an answer. Cut the shape and write electron pair geometry. Electron pair geometry. Geometry is also not correct. You have to say electron pair geometry. Then only it means. Now you can draw a structure like this, right? A suitable one for the tetrahedral electron pair geometry. And yeah, so how many electrons? 1, 2, 3, 4, 5, 6, and 7. So 7 electrons are there. 7 valence electrons. So 7 valence electrons are there in group 17. Answer is answer 4. Okay, there's a problem with the question. Okay, it should be actually answer all, right? But getting all is not useful here. So they must have corrected that one as electron pair geometry. You can see why it can't be tetrahedral, right? Because only 3 atoms are there. Okay, next question, 15. The compound which contains sulfur atom having the highest electronegativity is. Okay, good question. Sulfur with highest electronegativity. What you know is this line. Okay, electronegativity depends on of a given element depends on 4 factors. Okay, it's a hybridization state or the S character, then charge, oxidation number, and peripheral atom electronegativity. Just to get the idea here, let's draw these 5 molecules. Okay, so kind of try to arrange them in the ascending order. It will be valuable for you. Yes. Okay, so the molecules are SO2, H2S, and then SO3 2 minus, and then SO3 itself, and SO4 2 minus. These are the ions and molecules. So let's get their structures, bond structures. And H2S, it's like this, and SO3 2 minus, like this, and SO3 and SO4 2 minus. Okay, and then get this character. S percentage. S percentage is for this one. This is sp2 hybridized trigonal planar. Trigonal planar electron pair geometry. So sp2, if it is sp2, then S character is 33.3%. That's how you think and get. Okay, and this is tetrahedral, so electron pair geometry and sp3. So 25% is character. So this is also tetrahedral geometry, 25%, 33.3%, and 25%. Now you can see highest electronegativities should be therefore these two. Okay. And lowest for this, as this character is higher and electronegativity will be high. So what's the next point to compare now? Still from this character we can't get a final answer now. Then go to the charge. You can charge of sulfur, okay? Charge of sulfur. So you can see all these atoms are having no charge for the sulfur. So don't get confused here. It's not the -2 charge, it is there on the oxygen. So sulfur, there is no charge. So then go to the next point. Next point is oxidation number. And there's another one called peripheral atom electronegativity, which is not needed here. Let's get the answer with oxidation number. Here the oxidation number is +4 because it loses 4 electrons partially to the oxygen. Here the oxidation number is +6. So with a high oxidation number, it's asking the highest electronegativity. So this must be the one with the highest electronegativity. Answer is again 4. Always it is 4. Mostly it is 4 here in this paper. And then if you arrange them in ascending order, ascending order, highest electronegativity is SO3, then SO2, then what? Then we need to arrange these sp3 hybridized sulfur atoms, right? And if you check the oxidation number of this one, it is +6, and this one is +4, and this one is -2. No, yeah, -2. So then the arrangement will be SO4 2 minus, SO3 2 minus, and then H2S. H2S is the lowest electronegative sulfur. That's the lowest electronegative sulfur. Understood, Lama? Answer is answer 4. So write it as a review. So normally in A-level paper, they're asking you to arrange in ascending order. So will be a bit more challenging than this. Anyway, the same work you have to do. Okay. You can think and get the answer also, right? You can do. Yeah. Let's go to the 16th one. Give me a second, Lamai. I have to bring some water. Give me a second. Okay, 16th one. It's asking you to calculate the number of moles of phosphoric acid required to react completely with 25.65 grams of barium hydroxide. Yeah, the reaction is given balanced, right? Which you know in case how to do. So they react in 3:2 molar ratio. Okay, so barium hydroxide then H3PO4 phosphoric acid, they react in 3:2 ratio. That means 2 moles of this one should react with 3 moles of this. That's the use of ratio here. Okay, and it is telling the barium hydroxide mass. That means we have to, this ratio is applicable for moles, no? So then we need to find the moles of barium hydroxide. So first of all, molar mass of barium hydroxide. Molar mass of barium hydroxide. So how do we find it? Molar mass. So barium is given as 137. And there are 2 oxygen atoms, so 32. 2 hydrogen, it is 2. So 7 plus 4, 11, 1, 7, and 171 grams per mole. Now let's find moles of barium hydroxide. This is how you are going to answer it as an essay paper. Okay, I have teach you this part. 25.65 divided by 171 grams per mole. Yeah, let's try it and see, no? Is it divisible by some number? Can't say exactly. Anyway, let's try. We can't use calculators. So there will be 1.1 and 171. So it is 5, 50 minus 7, 85. Yeah, 85. Yes. Then you have this other 5 too. Okay, so now let's see. 171. 17 times 171 times 5. Let's take a guess and see. Okay, 5, 35, 3. It come. Okay, 0.15. So you have 0.15 moles. Made it a little bit difficult with the simplification, but still you can manage, right? Take a guess and see. Because I know 17 times 5 is 18, 85. That's what I used here. Okay. Then apply the ratio. Here, just simply asking the moles. 0.15 moles are there. So then, how many moles of this one? So how do we get that? And simply direct proportions. So divide by its own stoichiometry and multiply by the required stoichiometry. Okay, divide by own, multiply by required. Okay, so then it is 0.05. It is 0.10. Okay, 3 to 2 ratio. So this is your answer. If you are writing an essay paper, you have to write the ratio in the next line, then write the phosphoric moles. Okay, so but I showed that here. So answer is going to be 4, right? 4. Okay. Question number 16. Not a difficult one, but still somewhat good. Okay. Yeah, now let's go to the 17th. The response which contain only the species with the shape similar to XeO2F2. XeO2F2. Now let's draw XeO2F2 and see. XeO2F2. Now I'm not going to use the Lewis method here. So XeO2F2. Now let's see the shorter method. But what you know is you have 8 valence electrons with xenon. Okay, from that 8, there's no charge, no. So all 2 oxygen atoms are making double bonds. For that, you have to subtract 4 electrons to make 2 double bonds with oxygen. And from the valence electrons of xenon, okay. And fluorine makes single bonds. So there are 2 such single bonds. So subtract another 2. So then you will be left with 2 remaining electrons. That is what will be there as 1 lone pair. If you try to draw the structure now, there will be 2 xenon oxygen double bonds, and there will be 2 fluorine atoms and 1 lone pair. So around this one, you have altogether 5 repulsion units. They're asking about the shape, right? So 1 lone pair, 4 bond pairs, and altogether 5 VSEPR units. So it is trigonal bipyramidal electron pair geometry, and then seesaw shape. Seesaw shape is the shape. Okay, so seesaw shape. How do we draw it? You can put fluorine if you want here. Like this. They are in the same plane. Right, then you can do the same thing for the other molecules and see which one is having contain only species with seesaw shape. Yeah, you can eliminate the answers. Yeah, but I think we need to somehow try to draw, no? We'll see. We'll see. So the molecules are, there are several different molecules. We have XeF4, and then we have XeF2, and ICl3. I think we have a shortcut. Let's see. SCl4, ICl3 is again repeated. IO2Cl2 minus, XeOF3, and ICl4 minus. Okay, you have several more. If you try to draw them all, still you can get the answer. But let me suggest you a shortcut to eliminate some answers. Okay, So you can see to become CSO, it must have at least 4 bond pairs. To make 4 bond pairs, you should have 4 peripheral atoms, 4 terminal atoms, 4 terminal atoms. Okay. So then check these answers. This has 4 terminal atoms. Okay. This doesn't have 4 terminal atoms, so it's never going to be CSO. Don't try to draw this. This is also not going to be CSO. This is okay. This is okay, and this is also okay. Now you can eliminate 2 answers. Answers that are containing XCF2 and ICL3. So answer 1 is wrong. And then answer 3 is also wrong. And answer 5 is also wrong. You're getting lucky. And yeah, that's it. Okay. So these answers are wrong because of these answers, right? So don't try to draw them. Now to select the answer from 2 or 4, so you can see this structure is common for both the answers. So don't try that. So it's anyway not going to give you the answer. And then you have SCl4, XCF4, others are different. XeOF3 plus, no? It's a plus charge also. Right. Now draw one of these structures. Okay, you can draw and see any structure you like. I mean, from these structures. This one, this one, this one, or this one. There are 4 structures. Not this one. SCl4 and XeOF3 plus, and then XCF4 is there. And then ICl4 minus. So there are 4 structures. Draw one and see. Okay, because all 4 are different. No? So then if you see any answer which is, if you, let's say you draw this one. If this becomes CSO, then this is the answer that is containing this must be the answer. Okay, so you can see the idea. No need to draw the whole molecules. Okay, that is a shortcut and it's a good question for the A levels too. I'm really happy about this question. See, we got the structure of only one, they are telling. Okay, and then we look into the answers and we eliminate the ones with less than 4 atoms. And then you can eliminate 3 answers. Okay, and then only 2 answers are remaining, 2 and 4. This structure is common, so ignore that one. All other 4 structures given are different. So then you can try 1 and see. If it is giving CSO, then that is the answer. If it is not, then the other one is answer. Okay, so ICl4 minus. So iodine, I'll take this one. Iodine has 7 valence electrons. From that, chlorine makes 1 bond. So 4 you have to subtract and add another one for the negative charge. Altogether you have 4 electrons. That means 2 lone pairs. If you have 2 lone pairs, it's never going to be C-zone. So then this is not correct. So the answer that contains ICl4 minus is wrong. So answer 4 is wrong. Answer 2 must be the correct one. Okay, and draw answer 2 and see. Hardly it can be all, right? And what is the shape of ICl4? It is square plane. ICl4 minus. Square plane. ICl4 minus is square plane. Okay. Right. So there are other answers in the answer 2. Let's try to draw them and see. Other answers in answer 4. Answer 2. SCl4. SCl4 is just like SF4. Okay, it's going to be CSO. CSO. And the other structure is IO2Cl2. IO2Cl2 minus. There's a lone pair and there'll be 8 electrons around this siding. That's why the negative charge is there. And then XeOF3. Yeah. 1, 2, 3, 4, 5, 6, 7, and there's a plus charge. Yeah, correct. All are CSO. Okay, I hope you understood the method. get some practice. Do more questions and see your time test will maybe similar to this, right? So practice more. Yeah, 18th question. 18th question. The energy required to break the bond in 1 mole of Cl2 molecules is 245.0 kilojoules. It's asking the frequency of the radiation used to break. Okay. So here they have given energy for 1 mole. But we know, so anyway, first of all, this energy necessary to break the bond, here we are taking, assuming it is supplied by an electromagnetic radiation. Okay, so electromagnetic radiations carry photons. So then 1 photon breaks 1 bond. Okay, so write that. 1 photon break 1 bond. So then this much of 1 mole of Cl2 molecules, that means here you have 1 mole of photons. So then 245 kilojoules is the energy of 1 mole of photons. Okay, so energy is equal to h nu equal hc over lambda. Okay, and we are using this one. They are asking frequency. So energy of 1 mole of photons is h frequency into Avogadro number. Okay, and you can find this one by using wavelength and then find frequency, but it's a kind of a long path. No? So here your frequency is equal to energy of 1 mole over h into Avogadro number. So 2.45 into 10 to the power 5 joules, because 245 kilojoule mean 245 into 10 to the power 3 joules. So then I change it. Easy for the simplification. And Planck constant here, it is asking you to get 6 into 10 to the power minus 34 joule second. So Avogadro number, Planck constant is this one. Avogadro number is 6.022 into 10 to the power 23, but let's take it as 623. Okay, so if you want here per mole, then you can write per mole here. Then Avogadro number is also written for per mole. Then it's perfect. Yeah. So let's take this 235 itself, because anyway there's 2 6s. 245. Okay, so if you simplify this one, it is going to be 10 to the power minus 34, 23, 10 to the power minus 9. Sorry, minus 11. Sorry, minus 9. Minus 9. And here 10 to the power 3. So then if you simplify these two, it will give you 10 to the power minus 12. Minus 12. And 245 and 6. You can simplify. 245, you can roughly say it is somewhere around 4 point something. Okay, and if you divide this one by 6, it's approximately take the answer. Yeah, you can divide again by 2, 2 and 3. So it's actually 1.5 into 10 to the power minus 12, somewhere around Hertz value will come. And I think it is not there in the answers, because I kind of changed the answers. I changed the question when I'm typing the question. So in the actual paper, what they have given, that I thought about, it is from per mole. That's why I added the answer quickly. Added the 1 mole there quickly. But seems like it is not for the 1 mole, right? And this is not realistic somehow. So you have to cut the 1 mole and get the answer. So there will be an answer according to that. So if you cut the 1 mole and do the answer question, now like they gave in the paper, right? So then it is equal h nu. Okay, so frequency is simply equal energy over Planck constant. Energy over Planck constant. Let's do it and see. Energy 245 into 10 to the power 3. Here is 6 into 10 to the power minus 34 joule second. And you can see it's almost 4 something, around 4 something, around 40 something. And 10 to the power minus 37. And if it is 4 point something, around 4 something, it is 10 to the power minus 36 hertz. And there is an answer starting from 36. I know 37. I know 40 something. Yeah. It should be something greater than 40, right? Greater than 40. So, yeah, this answer is there. 42.5 into 10 to the power 37 hertz. 10 to the power 37 hertz. Sorry, it's not minus 37, it's just 37. So, answer is answer 5. If you cut the mole, but this answer is not, question is not realistic. That's why I added it. Usually ask for per mole, and this is a suitable answer. Okay, but it's not given. Anyway, don't worry. You have to do it according to the question. You can't change the question like I did, no? Okay, right. So anyway, you have to go with the answer. Answer 5. Okay, now let's go to the question number 90. It's asking for you to select the species with shape different from the other species. Okay, the one that is having a shape different from the other species. So what is that? So let's try and draw their shapes. You have O3. O3 is having is the Lewis structure of bond structure of ozone, and it is a bent shape, bent or angular shape. And then F2O, oxygen is the central atom. It is also bent, but the angles are not the same because they derive from two different geometries. First one is from trigonal planar geometry, and the second one is from tetrahedral geometry. HOCl. This is the structure. You can see it's kind of similar to the one we draw earlier. So that is also bent. And NH2 minus, there will be a lone pair, two lone pairs. So again, it's also bent. So all four structures are bent. Then you see the last one. IF4 minus, IF2 minus. Yeah, it's a linear shaped molecule that derived from trigonal bipyramidal electron pair geometry. This is linear. Okay. So this is our answer. Answer 5. Okay, so ozone and others, they have the same name, but this one is having different electron pair geometry. Okay, mark that too. Answer is answer 5. They're asking for the shape. So linear is a whole new word. Okay, the next one, 20th one. 25 centimeter cube portion of sodium carbonate was titrated with 1 mole of HCl solution. And it says 1 mole per decimeter cube of HCl solution, and 15 cubic centimeters was consumed for this titration. And it's asking how many moles are there in 1000 cubic centimeters of solution. Okay, we'll see. And they have given the balanced chemical reaction too. Let's see how to use it. First of all, you can see the ratio, just like for the earlier question. Sodium carbonate to HCl ratio is 1:2. 1:2. So we know the moles of HCl. Moles of HCl. So multiply the concentration into volume. 1 mole per decimeter cube and 15 centimeter cube. You convert it into decimeter cube like this. So it is 1.5 into 10 to the power minus 2 moles. Okay, so that amount is there, moles are there here. And then half of that will be there for the sodium carbonate, right? So you are using the ratio. And half is what? 0.75. Okay, 0.75 into 10 to the power minus 2 moles are there. So that 0.75 into 10 to the power minus 2 moles were there in how much volume? 25 cubic centimeters. So they're asking how much will be there in 1000 centimeter cube. So you are simply multiplying. Okay. So now let's simplify and see. 10 is remaining. So 7.5 division 25. 7.5 division 25. Okay. So it's divisible 0.3 moles. Okay. So answer is answer 2. Answer is answer 2. Okay, Lama. Not a difficult question, right? Just get the moles and compare it with the ratios. So if you are doing an essay question, you have to write a bit more for this question, okay? Answer is answer 3. Answer 2, sorry. 0.3 mole is the answer. Now we are going to there are only 5 questions left. Well, let's discuss them anyway. And these 3 questions are from ABCD, okay? So look at the first one. Correct statement regarding thiosulfate. Thiosulfate is R. So let's draw the thiosulfate ion and discuss. H2O3 2 minus. So you need to memorize the structure of this one. Okay, it will be important in inorganic chemistry too. There are 2 sulfur atoms that are bonded with each other. And there are 2 oxygen with lone pairs. So this is the skeleton structure and the Lewis structure. Okay. Now check the answers. The shape around the central atom is tetrahedral. The shape around the central atom is tetrahedral. So A is correct. Because there are no lone pairs. No? So 4 BSCPR units and no lone pairs. So it is tetrahedral. Second one, B. Oxidation number of both sulfur atoms are equal. So that's not correct. If you check the oxidation number, you are marking dipole moments. No? So here 4 electrons are partially lost. Okay. So the oxidation number of this sulfur is +4. Oxidation number of this sulfur, there's no losing or gaining. So oxidation number is 0. But if you apply mathematical method for this one, we're writing like 2x plus minus 2 into 3 equal to the charge, no? So then 2x minus 6 equal minus 2, 2x equal +4, and x equal +2. So that is an average value you can see now. What is the average of 4 and 0? 2. Okay, so this is the average oxidation number. So don't get confused here. Actual oxidation numbers are different. Then look at the C statement. The number of bonded electrons and number of non-bonded electrons are equal. So if you count the electrons, non-bonded, the lone pairs, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 lone pairs are there. And then check how many bond electrons are there. Don't say bond pairs. So you have 1, 2, 3, 4, 5, 6 bonds. That means 12 bond electron number of, what they're asking, bonded electrons. So 12 into 2, 24. Here 10 into 2 non-bonded electrons. So 20 and 24, it's wrong. It's not equal. Okay, from the structure you can take it. And D, the central atom is sp2 hybridized. No, it is also wrong. Central atom is sp3 hybridized. It is tetrahedral. Because of tetrahedral, you can say it is sp3. So then only A is correct. So other combination, answer is answer 5. Answer is answer 5 for this question. Okay. Only A is correct. Others are wrong. Others are wrong. Okay. Now let's do the next question. 22. It's about cathode rays, anode rays. There's no question in this paper from those, the basic, the things we discussed in the very first day. The incorrect statement regarding cathode rays and positive rays is A. So cathode rays and positive rays, two different things. Okay. Cathode rays and positive rays can move a paddle wheel placed in their path. That is correct. You can say, write this one. A is correct. Why? Okay. Remember, they are asking incorrect ones. Don't get confused at the end. A is correct. Let's first of all select correct and incorrect things. A is correct. Why? Because these particles are having a kinetic energy, a momentum. So they can turn the paddle wheel in their path, because when these particles, electrons, cathode rays are electrons, positive rays are nuclei of atoms. When they collide on the paddle wheel start to rotate. Okay, so then A is correct. Understood? So right, cathode rays are electrons. So electrons has a mass. Then positive rays are nuclei. So if it is the hydrogen gas inserted, positive rays will be H plus. If it is oxygen gas, it will be O plus, like that. Okay, O plus and can be other positive ions too, but of oxygen. But anyway, you can see it's different. The masses are different for positive rays. But however, they have a mass, no? So then can turn the paddle wheel by transferring the kinetic energy. So A is correct. B, since positive rays are positively charged, of course, yes, and they show equal deflection in a magnetic field, regardless the gas taken in the discharge tube. That is wrong. Okay, so like I said, if you take hydrogen gas, positive rays is H plus. If you take oxygen gas, positive rays will be O plus. So two masses, okay, their weights are different. So angle of deflection will be different. Okay, angle of deflection will be different for different types of positive rays. Okay, write that as a theory point. So B is wrong. Okay, A correct, B wrong, right? Angle of deflection will be different for different types of positive rays. Okay, so B is incorrect. Now look at the C statement. Although positive rays are a beam of particles having a mass like cathode rays, that is wrong. Cathode rays are electrons, so their mass is very, very smaller. So you can now see A was correct, B and C both are wrong. Okay, so underline that mass like cathode rays part and say it is wrong. And they do not show wave properties. That also wrong. So they both particles, basically anything can show wave properties, wave particle dual behavior. Okay, so it's a good question. See, so there are two mistakes in the C statement. What are they? Telling that positive rays mass is equal to cathode rays. Okay, and the other part is telling that they don't show wave properties. That's wrong. All particles can show wave properties. The thing is, for the macroscopic objects like baseball or something, wave particle wavelength is negligible when compared to its size. That's why we don't see them as waves moving, right? But electrons and these positive rays particles, those are very small particles, right? So when compared to their size, their wavelength is considerable. Okay, so now A was correct, B and C were wrong. And D statement, cathode rays and positive rays travel in straight lines. That is correct. Okay, so you can put a metal cross in their path and check this one. Remember. So they're asking the incorrect one. So incorrect answers are B and C. Here you can see B and C gives you answer 2. Okay, a good question. Then look at the 23rd question. The response which shows the correct increasing order of the property indicated in the parenthesis. So there was no question from radii, atomic, ionization energy in this paper. Okay, I think, anyway, there's one question here. Let's see whether it is correct. 23. So the first one, atomic radius, carbon, sulfur, phosphorus, arsenic, and selenium. So sulfur, phosphorus, arsenic, selenium, they are like this. And carbon is in this period. So in above period. So carbon is the smallest, that is okay. And then the radius is changing in the mirrored Z pattern. Remember this pattern. So selenium is the largest, then arsenic, then then it is sulfur. Here it is wrong. Okay. Phosphorus is smaller than sulfur. Okay. The correct order is carbon, phosphorus, sulfur, arsenic, and selenium. This is the correct order. Then look at the B statement. B state. It is for the first ionization energy, potassium, sodium, then phosphorus, magnesium, and aluminum. First ionization energy is lowest for the group 1 metals, that's correct. But this part is wrong. If you draw the third period, these elements are in the third period. So third period, across the period, they have this zigzag variation. Here it is sodium, magnesium, then aluminum. Aluminum is, they say is high, it's wrong. Aluminum is smaller than magnesium. Then you have silicon, then phosphorus. So you can see phosphorus is the highest. So that order is also wrong. So write the correct order. What is the correct order? Potassium is the lowest because potassium is larger than sodium, so it's easy to remove electrons than sodium. Then sodium. Then you have aluminium, magnesium, then phosphorus. This is the correct order. So both the statements were wrong, right? And the radius for the anions and their neutral atoms. It says fluorine, oxygen, F minus, O2 minus, and S2 minus. So this is actually correct. I'll explain why. This is a correct order. The reason is this. Okay. So as a point, we know anions are larger than their neutral atoms. Okay, because they have a negative electrical field. So not only for this one, we remember this N3 minus, O2 minus, F minus are larger than nitrogen, oxygen, and fluorine. Remember, then same thing they are for the cations too. Cations are smaller than their atoms. That means sodium, magnesium, aluminium will be larger than their cations, respective cations. Okay, so remember that theory point is a very special theory point. We must remember it was asked in 2020 A-level paper. And then this sulfur. So oxygen and sulfur they are in the same period, same group. So downward the group, radius increases. So it has more energy levels. So this is a good question, right? C is correct. Okay, and check the last one, D. Lithium, hydrogen, electronegativity. Okay, so these are, we have an order for the electronegativity. Remember, F, O, Cl, N, Br, bromine, iodine, sulfur, carbon, and phosphorus and hydrogen. This is the order. So this is the order that I ask you to remember for the electronegativity of nonmetals. Now hydrogen is here, okay, and then carbon is right here, and nitrogen is here, and oxygen is here. So those elements are okay, but lithium is not there because lithium is a metal. So always metal electronegativity will be lower than non-metal electronegativity. As a fact, we know it, right? Because metals are larger and like to lose electrons rather than gaining them. Okay, so lithium is the one with the lowest electronegativity. So then lithium, hydrogen, carbon, nitrogen, oxygen, this order is correct. I can see C and D answers are correct. A, B are wrong. They are asking for the correct ones, I believe. Yes. If C, D is correct, your answer is answer 3. Answer is answer 3. Is that clear, Lama? A, B are wrong. C, D are correct. Answer is answer 3. Okay, those 3 questions were really good. In this paper, it has some, majority good questions are there. No? Then look at the 24th question, true, false. A chlorine gaseous atom releases more energy than fluorine gaseous atom when gaining the first electron. That is very correct. And for the halogens, you can write their electron gain energies. For halogens, electron gain energies will be like this. Okay. Chlorine is the one that releases most energy. Then fluorine, then bromine, least energy is released by iodine. Okay, so you can say energy released during EG1. Now you are learning enthalpy, no? So you can say it is the negative value of delta H standard EG1, first electron gain enthalpy. Negative value ascending order, descending order. Or you can say this order is the decreasing order electron affinity. Electron affinity is likeliness to the electron. It's a long story if I go on to explain, but I'm not going to do it anyway. It's the opposite of electron gain energy. Right? So according to these facts, we know that chlorine is large. So first statement is correct. But what is the reason for this one before going to the second one? So the thing is, fluorine is very small and these are very large. Okay, so electron gaining is kind of difficult when they are very small and very large. So chlorine is the one with having optimum size. Optimum size. Okay, so it's good to take these electrons. So anyway, that is the reason about the sizes and something. Now check the second statement, what they are telling. The gained electron experience a higher repulsion because fluorine atom is small. Yeah, it explains why fluorine is lower. Chlorine is higher. So it haven't tell anything clearly about chlorine, but still we can get this as an explanation, right? Chlorine atom releases more energy than fluorine atom when gaining first electron. You must tell about chlorine to get a proper explanation. But still, we can put more weight to the explaining side. So let's take answer as 1. That means both are correct. Explain the first one. But few argue a little bit, can say that is not perfectly explaining too. Okay, but anyway, question like this, mostly we take answer 1. Okay, so here let's take answer 1. But remember, when you are asked to write a good explanation, tell about fluorine too. And fluorine experience a lesser repulsion because it is having an optimum size. Like that, you have to give more info. Okay. Now go to the last question. NO bond length in NO2Br molecule is equal. NO bond length in NO2Br molecule is equal. So now take NO2Br molecule. Let's draw it and see. It's a kind of a past paper related question. This is NO2Br molecule. That's a negative charge and there is a plus charge. Okay, again practice Lewis structures, okay? Then you can directly draw them quickly. And don't put another double bond, then it will violate the octet rule. So, NO bond length, is it equal? Now, if you just look at this structure, you may say it is not equal because one is a double bond and the other one is a single bond. But actually, this is not the real structure. Real structure is a resonance hybrid of these two structures, isn't it? So, if you consider the hybrid in resonance hybrid, you will notice that NO bond lengths are equal. There are partial pi bonds. Okay, so then this first statement is correct. You have to talk about the hybrid. So telling that equal is correct. Look at the second statement. If they tell about the resonance, then we can take answer 1. 2 acceptable resonance structures can be drawn for NO2Br molecule. Yes, that is correct. But the acceptable word is not good. Okay, so in A-level exam, they will not give acceptable because basically any resonance structure you draw is acceptable, right? Because it's following the Lewis method, Lewis rules. No? So it should be not acceptable, cut the word and write stable. Okay, 2 stable resonance structures can be drawn for NO2Br molecule, and that is the proper explanation. But anyway, let's take the answer as 1 by changing the question. But no point of keeping accept word there. Okay, it should be stable. Because the reason is this, you can draw an unstable structure too. Okay, you can draw an unstable structure too. In that structure, there will be a double bond between bromine and nitrogen. There will be 2 single bonds with oxygen. So this is unstable. Unstable, and it contributes a favor fraction for the hybrid. And these two are the stable. Stable. Let's say this contribute 40% to the hybrid. This also contribute 40% to the hybrid. Other 20% will be contributed by this. Okay, so still it is there, but you have to say stable. But even though it is there, it also contribute to the hybrid oxygen bond in the same amount. So you can see both bonds are equal. So then actually it's no problem. Okay, no problem. So the best answer is telling that there are 2 stable resonance structures. So those are the 25 MCQ answers and reviews. So actually some good questions were there and easy ones also there. But I think it's a good one that matching your A-level standards. Okay. Right. So let's do another paper in next week too. So I'm planning to do another school term test paper because these days you are preparing to the term test. Right. So you can get a great help from here. Because we already have done these things, you remember. We have done more difficult questions than this also, and we wrote 2 tests and 1 unit test and 20. This is paper number 22. So we have done a lot. So my advice is, while doing these papers, just make sure to go through all previous practice papers and test papers I gave you, because I have prepared them again using term test and past paper, those questions. So you'll get a good practice. Okay.